All right, so this is a fun little NMR problem that I came across, and I wanted to sort of talk through the strategy that I would use to come up with a plausible structure for a problem like this, and talk you through the thinking that I would have. So I see the chemical formula is given here, C8H16O2. I've got integrations and multiplicities for my different protons, and obviously my rough chemical shifts. The first thing that jumps out at me is this 9-high singlet, and there's really only one way to end up with a 9-high singlet, and that's something that looks like this. So these protons on these methyl groups, that will give us a 9-high singlet. This carbon here will be freely rotating, so all of these protons will be chemically equivalent. So we're going to get one signal for those protons. It should integrate to 9, so 3, 6, 9, and it should be a singlet. We should not have any splitting because this central carbon has no hydrogens on it. So that's the first thing that really pops, really jumps out at me. The next thing that I'm seeing here is a 3-high triplet. A really common way to get a 3-high triplet would be something like this. So these protons here, they should integrate to 3, the end of this methyl group. Anytime we see this sort of 3-high triplet, I'm immediately thinking sort of a terminal methyl group bonded to a methylene linker. So I've got a CH3 here, it should integrate to 3, and it should be a triplet because I've got 2 protons on the adjacent carbon. And this sort of strategy of breaking down each piece, that's what I'm going to do, right, until I figure out how to put everything together, basically. The next thing that I would look at would be these two 2-high triplets and a 2-high multiplet. When I see multiplet, the first thing that I think of, especially a 2-high multiplet, would be some sort of methylene linker like this. So this central CH2, that should integrate to 2. It should be a multiplet because we're going to get splitting from the CH2 group over here and also the CH3 group over here. And since I've chosen this as a CH2 group over here, I might think, well, does that fit with my 2-high triplet? And if this is bonded to something that is not a carbon with other hydrogens, it does fit, right? Because this right here should integrate to 2, and it should be a triplet based off of my splitting from my methylene linker here. So this CH2 here seems like it should be here. Now I need to start putting things together. So I think pretty clearly we're going to have this group here, and then this chain, my propyl chain right here, really takes care of these 3 peaks, but we need to put these 2 things together, and we also have 2 oxygens missing so far. We also, I think, should have, let's count, 1, 2, 3, 4, 5, 6, 7 carbons, and I need 1 extra carbon. So if I need to have a carbon plus 2 oxygens, to me, that suggests something like this, right? If I've got that carbonyl carbon bonded to another oxygen, then if I have this sort of in between, somewhere in here, that's going to sort of account for all of this NMR. So the question then becomes, do I have a C double bond O, or do I have an O then my C double bond O? So like sort of which order? So do I take this piece and put that in here, or do I have something that looks like this, and do I put that in over here? So which order am I going to put this thing together? Now, looking at the chemical shifts, and I think either of these are probably okay, but I think looking at the chemical shifts, one of these is definitely a better option. And to me, the better option looks like this. So where I've got, it's the C, CH3, 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 and then my oxygen here. And the reason I'm putting the oxygen here is because this shift, the chemical shift for this 2-high triplet, is not that far downfield. So the further downfield it would be, then I would say that maybe this oxygen comes here, so maybe these 2 switch places. But since it's about 2.4, 2.3, I think that the withdrawing effect is not the same. So CH2, CH2, CH3, I think this is the most plausible structure for this NMR. All right, hopefully that helps.